welcome everybody. So actually, before starting, I think on this occasion, I think it's really appropriate to thank the organizers for making this school happen. And we hope that this is actually the beginning of our coming back to our usual lives. So my name is Vincenzo. And I start apologizing because my handwriting is not as good as Leticia's. So, and you can reach me at this address. If you have any question, please contact me. So this course, so it's 4 lectures, and they will be about entanglement dynamics. In integrable systems. So actually most of these lectures will be about integrable models, but if I have time, I'll try to highlight some differences with the generic systems. So to begin with, I think it's a good idea to make a plan. So the plan is the following. So I'll start with a review of entanglement. Review. In many-body quantum systems. And here, actually, I would like to follow a different approach, not the usual one. So I would like to highlight the computational importance of entanglement. So the main idea that you should take is that somehow entanglement somehow is a measure of the complexity of the physical systems, okay? Complexity of and here both complexity and measures you should really I mean really in a loose sense, okay? It will become more precise later, but at this level is very, very wide. So practically what I will do here, I will introduce to some quantities which are called entanglement witnesses, which somehow are good entanglement measures, okay? So I'm sure many of you know quantities like the von Neumann entropy or any entropies, things like that. So then I think I would like to go to proceed by summarizing some aspects of out of equilibrium dynamics, out of equilibrium systems. Here I'll try to be quick because both Giuseppe and Leticia gave wonderful introductions. And in particular, I would like to stress one point that somehow entanglement is a very nice quantity because it allows you to understand that there is a deep interplay between our idea of statistical mechanics and quantum mechanics. Somehow the two ideas are really deeply intertwined, and I hope you can appreciate this during the lectures. Here, actually, Giuseppe gave us a very good analogy. So out of equilibrium systems are like an orchestra, where there are many instruments that play together. So as a statistical physicist, however, we have a very peculiar way of looking at this orchestra. So we take usually a coarse-grained approach, and when you coarse-grain things, they average out. So you get simple behaviors that are the ones that we describe with statistical mechanics. Somehow, somehow you see the picture loses a bit of the poetry. So the goal here is to recover some of the poetry, because you can see actually that looking at entanglement, you have the possibility to look at coherent behavior between different instruments, okay? So there is some quantum correlation that survives, and entanglement gives us a way to look at this deep correlation, okay? Good. So then the main part of the talk is about, as I said, entanglement dynamics. In integrable systems. So here, in this part, I will introduce the main idea, so the main tool, which is, it goes under several names, but one name is quasi-particle picture. So I will explain what this is, but in few words. So the defining property of integrable systems is that you have quasi-particles, single particle-like excitations, like solitons, as Giuseppe was mentioning today. And a remarkable fact is that you can describe the entanglement dynamics, so entanglement is a purely quantum concept, in terms of the propagation of these quasi-particles, which move around the system as free classical particles, okay? And if you want, this quasi-particle picture is at the foundation of something that you might call hydrodynamic approach. Dynamic approach for entanglement spreading. So the goal is to build this approach for generic integrable systems. However, even though systems can be integrable, it's still quite complicated to get numbers out of them. So here, to make our life easier, I will mostly consider free fermionic models. Free fermion models. So I will expand this quasi-particle picture for free fermion models. And then at the end, I will tell you how to modify what are the ingredients that you need to put to describe generic integrable interacting systems. So generic integrable. And then, depending on how much time I have, I will illustrate some new, more recent developments. Okay. Now, references. So there are some reviews already, mostly by Pasquale. So Pasquale Calabrese. Yeah, my handwriting is really horrible. So there is one which is archive 2008, 11/080. Yeah, there is another one, same author. Fisica A 504 3144 2018. And then there is a more technically, if you want, complex paper where you can find all the details. This is myself and Pasquale. And this published in SciPost. Okay. So let's start. Let's start with talking about entanglement in quantum many-body systems. So entanglement in quantum many-body systems. Here there are also a lot of excellent reviews. So there is a classic one by Amico et al. So it's a review of modern physics. And it's 2008. Yes. And then actually there is a special issue of JFSA, 2009. So there is, and one of the editors is here because it was Benjamin. And this is really a collection of excellent papers. So they are all very readable, interesting. So there is a special issue of JFSA. And this is 2009. And there is also a more recent review which focuses more on the condensed matter aspects. So this is Nicolas Laflorency. And this is physics report. Physics report. And this, let's see, C431, 2016. Okay, so what is the key question? So key question. So you are given a system, which I call S, okay? It's a system described by quantum mechanics, so a quantum mechanical system. Then you take a subsystem A. So the system is S, A plus is complement, A bar. And then you ask yourself, what is the quantum correlation between these two parts, A with the rest? So what is the physical intuition? So you want to know if you perform a measurement on, let's say, A bar, how much A is affected, okay? So let's say that the system is described by a quantum mechanical, by a wave function of psi. Of course, if you can write this as a tensor product, okay, the two systems are completely decoupled. So of course, if you perform something on A, this doesn't affect the remaining part A bar. So entanglement somehow tells you how far you are from this situation. Okay, so let me be very concrete. So to be concrete, let us consider a spin 1/2 system. Okay, we have actually, let's focus on a one-dimensional system. So we have a one-dimensional system, let's say with 5 sides. Now, so let's divide the system into 2 parts. So let's take the first 3 sides. This is our subsystem A, and this is the remaining 2 sides are my subsystem A bar. So on each side, there is a spin 1/2 variable, like Letitia. So this is quantum, though. So on each side, your variable can take values up or down. Good. So and this, of course, can be generalized to, you don't need the lattice. You can do it for field theory as well. Okay. Okay, now you realize that, let's say that your system is written, is described by a wave function psi. So you can write this wave function in this way. So you have to sum over sigma 1, sigma 2, up to sigma L. Let's say that my system has L sites. Good. Now you have here you have an object which I denote with T, and which depends on these variables, sigma 1, sigma 2, up to sigma L. And then I have my state, my quantum mechanical state. Okay. Now you see any wave function can be expanded in this way. Okay. The full complexity of the quantum mechanical state is encoded in this object here, which is a tensor, with the L indices. So you see that any state it can be expanded like this. So for instance, if you have a singlet state, okay, square root of 2. So this basically corresponds to taking this tensor in this form, in this way. So equal to 0. Then you have T up down equal to T, minus T down up equal to 1 square root of 2. Okay. And then you see that this choice basically corresponds to a singlet. Okay. Actually, it's very convenient to have a graphical interpretation of this object. So from now on, let's make this correspondence. So this object you can write in this way. So is this horrible blob with these legs sticking out, which denote these variables sigmas. Okay, now we can do the following. So our system is divided into two parts, right? So we can choose an orthonormal basis for the A part. Okay, so and an orthonormal basis for the B part, for the A bar part. Okay, this you can always do. You can choose a basis, orthonormal basis for A and for A bar. This index is J. So if your subsystem A has length L, this indices A take values up to 2 to the L, and in A bar 2 to the L minus L. Okay? So actually this is important. If you look at this object, if you want to describe a generic wave function, you need the 2 to the capital L numbers. This is a humongous number, okay? We cannot deal with it in practice in any realistic situation. Okay, let's proceed. So what do we do next? So we have our psi, and this we can write in this way. Okay, so we expand our wave function of psi using this basis, psi A and psi A bar. And this is a definition, if you want, of this matrix M that we have here. Now, the full complexity of the state is encoded in this matrix. Now you have a matrix. So if you work with the quantum information people, when you have a matrix, what do? So you singular value decompose it. Okay, so what is a singular value decomposition? So singular value decomposition, SVD for short. So what is that? You can open Wikipedia, and then you discover that, so for a generic matrix, which has not to be square, which is, let's say, m times n matrix, you can always do this. Okay? You can always decompose it in this way, where this sigma is diagonal. So sigma is, well, whatever. And the elements of the diagonal, for convenience, I write them in this way, okay, as a square root of some numbers. And then this u and v are unitaries, okay? What do you mean, how many? It's the minimum of the two dimensions. Yeah. Okay. Now you can apply this blindly to our wave function, to our matrix mjk, and what you get is the following. What you get is that now your state psi is decomposed in this way. Sum over alpha, square root of lambda alpha, and then you have a okay, you have now your matrix, if you want, is is diagonal. So you have only one index, which is alpha. So apparently you gain something, and this psi tilde are basically obtained by applying these matrices to the original basis. Okay, so for instance, psi tilde A, you get it by applying u to the original vector of psi's. So so far this is this is exact. So we didn't gain anything except that we have only one sum, but this index alpha still runs over an exponential large number of values, right? Graphically, you can picture this in this way. So you have your original blob, and this now became this thing here. Sigma 1, sigma L. Okay. And this leg here stands for this sum over alpha. And these two blobs are these two objects. Still, we didn't do much. What we can do now, so is to look at these numbers here. You take your wave function, you look at these numbers, and then you look how they decay. You can order them according to their magnitude, and you look how they decay. If they decay sufficiently fast, you can imagine of discarding the smaller ones, and this gives you an efficient representation of this tensor. And actually, so for ground states of local Hamiltonians in one dimension, this can be done very efficiently, okay? And this is what is the basis of DMRG, density matrix and normalization group, which is really the method of choice if you work with the equilibrium and out of equilibrium problems in one dimension. Actually, there is a nice review by Uli Scholwok, which is in Annals of Physics, 32796, and it's 2011, yes. Okay. Now you see that actually, again, the complexity of your wave function is encoded in these lambdas. So if your wave function can be written as a product state, it means that you have only one of these lambdas, which is equal to 1 because the state has to be normalized. So the more these values are evenly distributed, the more entanglement you have in your system. Yeah. Ah, sorry, here is sigma L plus 1. Yeah, sorry, I forgot the sigma. And this is sigma L. Yeah, the last one is, yeah, thanks. Actually, so you can take this object and you can keep going with this decomposition, okay? So you can start from this, and then you can singular value taking only the first index, okay? And then if you iterate starting from here, you go to this, and so on. And then in the end, if you keep going, what you end up with is the following. So you end up with this structure. So you have L legs, which are the usual, the spin indices that you had at the beginning. And then you have summations over these horizontal legs, which are called virtual indices. And this is a matrix product state, okay? This is called matrix product states. So it's a useful concept that I think everybody should be familiar with. Now, you remember, yes?
I remember at the very beginning of the subject a lot of paradox.
Mm-hmm.
But in particular, if you take the antisymmetric combination, definitely we are entangled. This
Mm-hmm.
maybe definition of entanglement.
Yeah.
But to take the symmetric one,
Mm-hmm.
is a question of basis. I can rotate the system and go from spin 0 to spin 1.
Yeah, one is the spin 0 member of the triplet.
But your definition seems they are entangled. Okay.
They are entangled. Yeah.
I can write as a tensor product and the other two.
Of course, you have to choose. You have to keep the basis. Yeah, you have to fix a basis. Yeah. Yeah, it's not everything is basis dependent, but many things are. Yeah. Mm. I mean, you can always take the basis, rotate it, and this shouldn't affect because it's what you work with in the end is the spectrum of an Hamiltonian, of a matrix, and the rotation would be. I mean, it's just a rotation, so it doesn't affect the spectrum. As long as you do this, it doesn't. Nothing changes. Of course, everything depends on the basis, also in the sense that you can work with the real space, or you can work with momentum. Of course, the two things are not the same. Yeah.
No, but I mean the symmetric one, I mean forget the X and P of the Eigens, but the spin, I rotated is entangled, I rotated is tensor. It's weird.
Yeah. Yeah, that's right. Yeah. Yeah. Yeah, that's a good point. Good. So I was saying that while you are doing the singular value decomposition, you imagine of truncate your tensors. So let's imagine that each time I do a singular value decomposition, I keep only the largest k singular values. So here there is a sum over k elements, and so on, k elements. So how many parameters do I have now? So it's k square, because each of these is a chi by chi matrix. And then I have this index, which takes two values. So I have 2. And then I have times L, because I have L matrices. And this, if you can keep chi small, is much smaller than 2 to the L, okay? So if you can use this kind of truncation, you really gain a lot. Good. Now, how do we connect this to the usual way entanglement is presented? So, yeah. It's exponential. If you are depends a bit on whether you are gapless or gapped. So for gapped, so entanglement saturates, it really they go very fast. For gapless, it's a power law, yeah, but it still allows you to work comfortably with the MRG. Okay, so what is the usual way entanglement is presented? So you have your system, your subsystem. Then you have to define the reduced density matrix for A. So you have your full system density matrix. And then you take the trace over A bar of rho. Now, if you use this decomposition here, you can immediately write down this rho A. It's a simple exercise, so you can do it. So rho A is equal to sum over alpha, then you have lambda alpha, and then you have this Now the reduced density matrix after this trick is diagonal, and this lambda alpha are the eigenvalues of the reduced density matrix. Okay. Okay, now a standard measure of entanglement is the von Neumann entropy, and this is defined as minus trace of rho A log of rho A, or in terms of these lambdas is minus sum over alpha, lambda alpha, log lambda alpha. Or you can use, alternatively, you can use the Rényi entropies, okay? So Rényi entropies are 1 minus n log of trace rho A to the n so these quantities. And you see they are related to these parameters lambdas that control how much we can truncate our quantum mechanical wave function. Okay? Yes, so yeah. Mm-hmm. Mm-hmm. Yes. Yeah. Yeah, it's I can be more precise in a second. Yeah. So actually, let's go back to this representation here. So how much entanglement can we store in this with this matrix product states? So basically, what we have is that so we have entanglement is contained in a matrix which is chi by chi, where chi is the number of singular values that we keep. What is the largest amount of entanglement that we can have is when this chi by chi matrix is diagonal and it has all the elements equal. Okay, so when the lambda i's, the lambda alphas are 1 over chi. If you have just one, you have a zero entanglement. If you have, if they are the same, you have the largest amount of entanglement possible. So what is this amount of entanglement? Well, you take the formula of von Neumann entropy, and you see that is log chi. So S, so the largest amount of entanglement that you can have with this decomposition, with this matrix product states, is log chi. If your system is gapped, this chi, or you can invert this, right? So you have that chi is e to the s. Now, if your system is gapped, this chi can be finite, okay? And because the entanglement saturates, you have a finite value of entanglement, which gives you a finite value of chi. If your system is critical in 1D, the entanglement entropy grows with the system size, with the subsystem size. However, in 1 dimension, even though you can be critical, this S grows at most as log L, where L is the size of A. And since you have a log here, it means that your chi, which is called bond dimension, doesn't have to grow much. I mean, it's still polynomial in L. So with the increasing polynomial in the bond dimension, you get a very accurate description of your state, even if you are even in this critical case. Of course, it's worse than the gap, right? But okay, good. So one thing that I should say is the following. So this is at equilibrium. What happens when you go out of equilibrium? Actually, is very different, because out of equilibrium, what you have, we will see that you have that S increases linearly with the time. And this means that if you put this S here, the bond dimension has to grow exponentially with time. So if you want to simulate out of equilibrium situations with the MRG, well, it's tough. But in many cases, many physical cases, it's still something, I mean, even though you can reach short times, you can still get the physics. In general, no, okay? Okay, so, yeah. Actually, how much time do I have? What? 20 minutes, okay, good. Mm-hmm. Yeah, of course. It saturates, yes. Yes, but in several cases, you want to take also the limit in which your subsystem becomes infinite, and then you have a linear growth forever. Yeah. So. Sorry? The saturation bound is it's volume with the subsystem size, which means it's yeah. So out of equilibrium. So here, actually, the main goal is to show that this reduced density matrix is a natural quantity to look at when you study out of equilibrium physics. So let me make a brief recap. Okay. So here, out of equilibrium means for me from now on quantum quenches. Okay. So let me go over it very quickly, because Giuseppe talked about it today. So we have a state, psi0, and we have an Hamiltonian. And the system is isolated, something that we should always stress. Everything is isolated, so you have that your system at a generic time t is evolved with this under this Hamiltonian. So this psi0 is not an eigenstate, so it's non-trivial. Now, so what do we see? So why, Giuseppe summarized already why this is important. Maybe one thing that I should stress is that if you look at the out of equilibrium dynamics, only if you look at local observables, what you see is that you see equilibration, right? Globally, of course, this is not possible. But if you look at local observables, you have equilibration. And moreover, you can describe in many situations this equilibrium or stationary behaviors with either with the usual statistical mechanics that we know, Gibbs ensemble, so Gibbs, or in 1D for integrable systems, generalizations of Gibbs ensemble. Generalized Gibbs ensemble. So an important point is that even though integrable systems are somehow strange, so we have an extensive number of conservation laws, the Hilbert space scales exponentially. So even if you fix all the conserved quantities, you still have an exponential large number of microstates in which your system can equilibrate. Now, why entanglement and the reduced density matrix is important? Well, because it gives you a way to define what you mean by equilibration. So we have our density matrix for the full system, okay? And then since we look at local observables, the natural object to look at is the reduced density matrix for subsystem A. Okay? This also evolves in a non-trivial way. Okay, so all equilibrium properties of local observables are encoded in this row A. And actually, let me give a more precise definition of equilibration. So we say that a system equilibrates if, when we consider an infinite system, okay? So given an infinite system, so we say that it equilibrates if an infinite system equilibrates if for any subsystems A, for any subsystem A, for any subsystem A, so the following limit exists, okay? T going to infinity, rho A of time, okay? Now, the most important thing here is that there is a precise ordering of limits, right? This is the thing which is most important. So you first send the total system size to infinity, then you send time to infinity, and then eventually you can also send the subsystem size to infinity. Okay, this is the usual way we define equilibration. Of course, you are allowed to take any limit that you want, but you, yeah. Mm-hmm. Yeah, that's right. There is, I think there is a uniform convergence on subsystem A. Yeah, I wanted to be precise, but you spotted the. Okay, thanks. Okay, right. As I was saying, I mean, you can also relax some of these assumptions, but you are not guaranteed that things go well. For instance, you can have recurrences if you have a finite system. Yeah. Sorry, what? No, this is because there is the order of limits, right? You cannot do that. Okay. Okay. Now, what do we mean by the fact that our system relaxes to a statistical ensemble? So we mean the following. So if we define the density matrix of the ensemble for the full system, like Laetitia was doing today, so this is statistical ensemble. Can be Gibbs or GG. So equilibration to this ensemble means that you have the so if you take your subsystem, your system is infinite, you take your subsystem, you go to infinite time, this relaxes to this density matrix, okay? And then this means that you describe your local properties of the system with this ensemble. So, okay, you can have, as I said, you can have rho Gibbs. Or you can have different ensembles, like generalized Gibbs ensembles. So let me. So the generalized Gibbs ensemble actually is the case that I'm interested in now. By the way, I should say that there are many physical situations where you violate the paradigm of thermalization. So Valentina will talk about another one, which is many-body localization. There are also quantum scars. There's all sorts of different behaviors. So here I consider a violation of paradigm of thermalization due to the fact that you have integrable systems in 1D. So GG and integrability. So in this case, as Giuseppe was mentioning today, so we have an extensive number of conservation laws, which I call I. So there is an index N, an index M. They all commute with each other. One of these is the Hamiltonian. And then you might imagine that for integrable systems, instead of the Gibbs ensemble, you might imagine that you have to include all these other conservation laws into the game, right? So you define a new ensemble where you have these extra conservation laws. Okay? Sorry, no. Let's call them beta, which looks more like temperature. Okay, so now all these i's are conserved, right? So basically, if you have your initial state, this quantity is constant in time, so it doesn't evolve. But if we demand that our local properties are described by an ensemble, this has to be equal to the ensemble expectation values of the charges. And this you can use to fix these betas, okay? This is not possible. You cannot use it. There are ways around it, okay? Well, Letitia can. Maybe you can. Yeah, yeah. For the spherical model, you can. Yes. So, so before concluding this part, actually, I would make a simple remark that so that this definition of integrability, of course, is problematic. We're asking? No. This definition of integrability is problematic because if you consider a generic quantum system, you always have can construct actually an exponentially large number of conserved quantities, which are basically the projectors over the eigenstates, right? If you have a given eigenstate, each projector is conserved. So, of course, you have an exponentially large number of conservation laws. So the question is, yeah. In principle possible, computationally impossible. I mean, to determine them, you have to solve a problem which whose complexity grows exponentially with the system size. So it's not, yeah. Mm-hmm. What do you mean? I don't understand what you mean, sorry. Yeah. I mean, yeah, but what matters, I think, is the density is not, they are like the Hamiltonian, right? It's a sum over some index and then an operator which is as compact support in the simplest case. Unfortunately, this is not general, right? Because I mean, you can try to take an integrable model and work only with local observables. You can construct a statistical ensemble like a GG. This is not enough. Okay, it can be shown that this is not enough. So to have the correct ensemble, you have also to consider charges that have not finite support, but have some quasi-local structure, which means an exponentially. Mm-hmm. My opinion is that actually this is not the right definition. Okay, so the definition that I like most is based on the concept of quasi-particle. So a generic thermodynamic macrostate which identifies a statistical ensemble is determined by the distribution of this quasi-particle. In fact, the approaches that people use to construct the GG, they go through the construction of this distribution of quasi-particles. Yeah, this, if you want, is what you would think is the natural way of defining equilibrium, basically, based on physical intuition that you need some locality. Yeah. Yeah.
What happens is that typically the value of the charges are enormous. So when you try to pose this system, you have the expectation value of this has to be some set of beta. Unfortunately, the landscape is so big that a minimal variation.
Yeah. The other one. Yeah, yeah.
You never find a beta set. So there exist many beta that is the same one, so means at the end is meaningless. So this is what happens.
Yeah. Yeah. Well, actually, I don't know about the construction in real space. They have to decay somehow, but I don't know if it's yeah, no. I don't know if this is known. Maybe Marco knows. Yeah, or yeah, or. Mm. Mm. No. No. Also because in many when you work with these objects, usually you work with their eigenvalues, so you can ignore their spatial structure. And then you just check that when you include more and more of them, just working with the eigenvalues, you see that you saturate. Yeah, and then you can compare with other approaches and see that you get to the correct ensemble. But actually, I'm not sure, maybe Marco knows better. So the spatial structure of them, of these local charges, is not, quasi-local charges is not really, at least not that I'm aware of. So, okay. Yeah. No, actually, I think it's a perfect time to stop here. Or maybe actually, if I may, I can say only one more thing. Yeah, so actually, the thing that I want to say is that it's very convenient also to get a physical intuition to work from a microcanonical point of view. So we introduced the GG, but we can think of the GG as emerging from a macrocanonical ensemble. So in the macrocanonical ensemble, you have the spectrum of the Hamiltonian that you use to have the dynamics. So this is the spectrum of the Hamiltonian H. Now, so let's imagine that we work only with for now with the Gibbs ensemble. So the Gibbs ensemble, you can think of the Gibbs ensemble as emerging from a macrocanonical average, okay? So the energy, if the energy is the only quantity that is preserved, you can choose a macrocanonical window here with the value of energy, which is fixed by the value of the Hamiltonian in the initial state, right? And then what will happen is that as you go to the thermodynamic limit, all the eigenstates in this macrocanonical window will give the same expectation values for local or quasi-local observables, as Giuseppe was saying this morning. So this is the eigenstate thermalization hypothesis. And you can do the same for the GG. So for the GG, you have to consider a multidimensional macrocanonical window in which you fix all these conserved quantities. So, and what happens is that as you go to the thermodynamic limit again, all the eigenstates in this multidimensional window will give the same expectation value of local observables. So technically speaking, they will give rise to the same macrocanonical state, okay? So, and all expectation values will be the same as the ones that you obtain from the GG, okay? So I think I will use again later this idea, okay, to derive some of the results. Okay, thanks.